Hey, hello guys, welcome, vanakkam, vandanam, namaskaram. Today we are going to see relations and functions first part. Okay, see last time about mathematics, if you're checking, we have uploaded determinants video. Okay, still there is a 15 minutes video that has to be uploaded based on determinants. Matrix I haven't even uploaded even a single video, but now we are going with relations and functions. Okay, so before get going with this topic, I want to introduce someone to you, that is my pet bird, who is Pikachu, who is known as Pikachu. Well, its breed is going to be pineapple conure, one of the most friendly bird and a short-tempered plus aggressive bird, I can ever say. Bites very hardly. Okay, well, yeah, in some of my videos you'll be seeing my pets. I also have a hamster, but unfortunately I cannot bring hamster to my videos. Like, if I have it like this and if I'm teaching over there, then the hamster will fall. Okay. Now let's proceed with this lesson, which is relations and functions. Okay, perfect. So in this, already we have seen this lesson, right? In our class 11th even, we have seen about this lesson very well. But we will have to do a little bit of revision here and there. I will be saying what's a function, when it will be a function, what's a relation, okay, what's the difference between a relation and a function, then what is the basic of all of them, like Cartesian product, all of those things is I will be explaining to you, okay. Well, Cartesian. First, we will first check the relation between relation function and Cartesian product. Okay. Well, we are just checking out. Okay. So let us assume that this circle is what Cartesian product is. I'm very sorry for the noise. I will try my level best to give the clear clarity of my voice and my bird's voice. Okay. So this circle is Cartesian product. I'll just write CP. Okay, Cartesian product. Then the circle which is inside the circle is actually going to be no. Okay, so this circle, let's assume that this circle is actually relations. Okay, so this circle is relations. Just R is enough in order to represent relation, I think. Okay, then the circle which is inside of this circle, let's assume that this circle is function. Okay. This circle is function. So from this we can say that Cartesian product is the very base point of this lesson itself. Okay. So first we have to learn what is a Cartesian product. Then we have to learn what's a relation. Then we have to learn what's a function. Shh. Nothing. Okay. Be quiet. Okay. So first we. Shh. Once again. I think problem has got settled. Now we will be proceeding back. Okay, so first we have to know what is a Cartesian product. First we will be knowing what's an ordered pair. Okay, what is an ordered pair? You know. Okay. You are actually arranging two similar things. Okay, you are actually arranging two similar things in between closed brackets by splitting them with a comma. That is what we'll be saying as ordered pair. Okay, well, this definition is not required. They won't ask a definition at all in mathematics. Well, for an example, 1 comma 2 is an ordered pair where this first element represents the x-axis. Okay, so this element actually represents the x-axis. Okay, and in this second element represents the y-axis. Okay, normally this is how it happens. Okay, and super. So just one or two basic things that I have to say. That is, for an example, 1 comma car. Okay, 1 comma car cannot be an ordered pair. Okay, 1 comma car cannot be an ordered pair. Same, see, car comma bike can be an ordered pair. Okay, because these two are similar things, but 1 comma car isn't a similar thing. Okay, so since these two are similar things, we can say that it is an ordered pair. But here, one is completely different from a car. Car is a vehicle that is used for transportation, right? And one is a number, so it cannot be an ordered pair. Okay. And also, here I have said, right, this car comma bike. Numbers normally represent the x comma y axis. Okay, so numbers normally represents the x comma y axis, but whereas bike and car cannot represent x and y axis. Okay, so it's like this only. So in this, if they are given something like this, okay, it's not an equation, a relation like this. Now then that means x is equal to 1, comma y is equal to 2. This you have to know. Okay, this is very basic thing we have already studied in our class 11th itself. Perfect. Now coming to graph. For an example, let's say that. Okay. Okay, like this it is. So let me assume that, okay, see, let me assume that I will be taking a few lines, sorry, few points in this graph. So let this point be x point. Okay, let this point be y point. Okay, let this point be a point. Let this point be b point, and let this point be c point. Okay. So now I have given all the points. Now I'm going to just plot the graph. Okay. Okay, like this I'm plotting. So first for y I'm going to draw a line. Okay, so for y I'm going to draw this line. For x I'm drawing this line. For a I'm drawing this line. For b I'm drawing like this one, and c I'm drawing this line. Okay, so now I'm going to plot the graph for them. Like I've already plotted it, I'm just going to give the name for them, like this. See, for this I can say that a comma y, right? For this a comma x. For this b comma x. For this b comma y. For this c comma y. Okay, for this c comma x. So this is what their graph is going to be. Perfect. Since I have changed my room completely for video purposes, my bird is having some anxiety attack. Not an attack, just it's suffering with anxiety. Don't worry, it will get adapted to them very easily. So for this one, like why did I draw this one? See, this graph states that first I'll be taking a set. Okay, I'll be taking a set. I'll use another color. Let me use which color? This color I'll use. Okay, so let a set have x comma y. Okay, x comma y it can have. Okay, and let b set have. Let b set has. Okay, so let this set have a comma b comma c. Okay, so here b is having a comma b comma c. Here a is having x comma y. So here I'm going to just cross multiply. Like I'm going to do the Cartesian product. What is a Cartesian project? What is a Cartesian product? Yes. So what is a Cartesian product? Cartesian product is just multiplication of two different sets. Okay, so Cartesian product. For an example, here I'm going to just multiply a into b. I'll use another color. So a into b is what I'm going to do. So that means set a into set b, which is a comma b comma c. Okay, so here this means like if I'm just doing the multiplication, which uses x comma a, okay, a comma x, b comma c comma. Okay, so that means here I'm going to do it as b comma a. Okay, so since I'm going to do it as b into a. Okay, if I just multiply b into a, b, c. Okay, multiplied with x comma y. Okay, so if I'm multiplying here, how will I get? It will be no. Okay, it will be a comma x, a comma y, b comma x, b comma y, c comma x, c comma y. Okay, c comma y. That's it. I'm just going to shrink it a bit like this. Okay, well, sorry for just unwanted timings. Okay, I have wasted a lot of timing. Yeah, so this is what a Cartesian product is. So if you're just checking it out, so this set, okay, here I've plotted this x and y, right? So this is going to be a set. Okay, so these two represents set A. Okay, and these three represents set B. So when you're multiplying B with A, you're going to get like this. Okay, so how about you are multiplying A with B? In that time, all you have to notice that, see, here I'm multiplying B into A, so I'm getting this as my Cartesian product. Okay, so when I do the opposite, then B has to go here and A has to come here. B has to go here and A has to come here. Here B is actually in the x-axis. Here A is in the y-axis. We will always write like this only now. X comma y only writing. X comma y. So see, this is over here. So here first set is going to be B. So first set, that set which you are multiplying, the first set has to be in the x-axis, and the second set has to be in y-axis, since it is like this. Okay, that's it. Very simple, right? Okay. This is what Cartesian product is. Just multiplication of two different sets. And Cartesian is a scientist. A mathematician. Okay, he is the person who has, who's literally the father of all these things. Is okay, geometry, all those. Okay. So we will be next going with we shall see about the relation. Okay, so what's a relation? So before going into relation, I want to just say a note point. Since we are in our class 12th standard, we have already studied the relations and function in our class 11th itself, right? So we need not go that much basic, but there are a few persons who may not know relations and function in our class 11th standard. So some points we'll be repeating, okay, which are very important. First, we'll be knowing one note thing, that is, every function is a relation, but not every function. Every function is a relation, but not every relation is a function. Okay, so this is something that you have to know. Every function is a relation, but every relation is not a function. Okay, it's not a function. This is something that you have to know. Okay, maybe if you are if you have understood the diagram that is here, even okay, this circle diagram is there, right? In class 11th there is name for this diagram. I forgot that name. Some name is there for this diagram. Okay, when you are drawing like this, there is some name. Okay, so with this diagram, even you could have found that every function is a relation, but not every relation is a function. That is what every function is a relation, but every relation is not a function. Okay, coming back to relation. Relation definition I'll first write. Okay, since definitions are very important. If you are pretty good in English, definitions itself are enough, literally to cover 40% of mathematical topics. Okay, so I think personally, I'm not a teacher, I'm just a student I just take seminars. So if there can be mistakes in my seminars, so even if you ask me, I will be suggesting to see some other professional teachers' videos only. Okay. So let A and B be two non-empty sets. A relation is defined as. Okay. Let first we will assume that let A and B be two non-empty sets. Okay. Be two non-empty sets. Okay. So in that sense, relation will be always a subset, or it will be directly equal to the multiplication of A into B. Okay, relation will be a subset, or it will be directly equal to the multiplication of A into B. So what does this symbol mean and what does this symbol mean? What's the difference between them? A lot of people doesn't know. A lot of persons doesn't know. It's actually pretty simple. So the thing is, see this symbol. This I will erase it because it is kind of basic thing. So this symbol and this symbol. What does it mean? In our class 11th and first lesson even we have studied about them. But it's okay. It's our nature to forget. Okay. Normally it's our nature to forget. So I'll just give you a little bit of revision about these two things. Yes. This means so this means that it contains. Contains. Okay. So this means that belongs to. This means that belongs to. Okay, belongs to. Here it means contains, here it means belongs to. This will be used to represent the subsets. Okay, and this will be used to represent the elements of the set. Okay, elements of the set. So always remember that. For an example, let me take a set. Okay, let me take a set called as A set. Okay, this is not over here. I'm just going to give it by my own set A. Okay. A is equal to 1, 2, 3, 4, 5. Okay, so here that means you can say that 1, 2, 3 is a subset. Okay, is a subset of A. Okay, it's a subset of A. Like that you can say it as. Okay, I'm so sorry. For some reason my bird just doesn't like my leg. I don't know why. Okay, so here next is belongs to element. So that means here I can say that 1 is an element of A. Okay, 1 is an element of A. Like that I can say. Okay, just 1 is an element of A. Okay, if you want to say that 1 is a subset of A, then you can write it as, you have to write it inside the special bracket and you have to put the symbol and then you have to write like this. Okay, va? That. So coming back to here in this topic, let me say that relation. Okay, this relation R is actually where A comma B, where this element comes from this set and this element comes from this set. Okay, so where you have to put a symbol like this, inverted A. A is actually A belongs to capital A and small b belongs to capital B. Okay, this is what it actually says, where this I said now, that is what is over here. Okay, so what does this capital inverted A say? Okay, this one says that okay, so this inverted A is there, right? So it means that for all. Okay, so for all A, for every A, okay, for every letter or for every element that is being written here, that belongs to set A. Okay, for every element or for every letter that is being written over here, that belongs to set B. That is what it means. Okay, done. So now we will be just get going with relations. Now they have given you this relation where R. Okay. So A plus 3B is equal to 12 is something that they have given. where for every a comma b, for every a comma b, it belongs to a natural number. Okay, it belongs to natural numbers. Okay, perfect, pakka, done. So what we are going to say here is that b is, yeah, okay, so first we'll be just starting. Okay, we'll just write this one. So see, a plus 3b is equal to 12. This is there, right? So this is the equation that they have given us. So based on this equation, you have to put numbers in that, and we have to take okay, so which is actually qualifying over there, and then we have to proceed. Okay, so since every natural number will be very big, okay, natural number less than 4, less than 5, like that we can keep it as. Okay. Or yeah, this is even enough. So here b is equal to, 12 minus a by 3. Like this it is there. So here it is very specific. We are very specific. Based on the input only, output is also there. See, for example, this is what a, always a comma b is the thing that we are writing, right? Okay. So first you are giving this a, okay, you are giving some value that is a, which is less than 4, okay, so which is less than 5. So that means it can be 1, 2, 3, 4. Okay, so these 4 numbers it can be. So first I'm giving some input to this a. After that input, based on that input only this b value is there. Okay, so for an example, let me say that for this a I'm going to give it as what? If I'm giving over there 1, so then it will be 11 by 3. Okay, then it will be 11 by 3. Then if I give some other elements like this, okay, for example, over here if I give 2, then it will be 10 by 3. If there is 3, then it will be 9 by 3, which is 3. Then if I give there over 4, then it will be 8 by 3. Like that, it just depends. So based on a only, this b values also. But the thing is, they have said that b should be also natural number. But this is not natural number. So one and only set that is there is, we can say it as 3. Okay. So if a is 3 now, okay, if a is 3 now, then automatically b is also 3 over here. Okay, wow. So I will just take this 5, since only 1 is there. Okay, since only 1 is there, I will just change this less than 5 with based on less than what, 9 shall I give? Okay, so less than 10. Okay, less than 10. Okay, wow. So then what we will be getting is that it can be 6 comma 2, and also it can be 9 comma 1. Okay, if you give here 9, then it will be automatically 1. If you give here 6, then automatically it will be 2. So like this, since it is less than 10, I have given all these, and this is what the output that I have got. Okay, but here you can say it as a relation. That is something you have to know. This particular is what actually the relation is. This set is there, right? So that set is what the relation is. You can say this set as a relation, or also you can say that this set as function. Okay, so this is also a function. Okay, very important is that here is the place where this sentence is being satisfied. Okay, so here this is a function and here this is a relation. Both are there. That's it. So what is actually a function, what is a relation? The difference is that, see here for a relation, this first element can repeat. Okay, this a element or this x element can repeat. This element can repeat in a relation. But for function, it will not repeat. If 3 is there, then in anywhere, okay, in anywhere you cannot find 3 in the first place. Maybe the second place, here you can see, but in the first place you cannot see. That is the x place, we can say, or in the first point, or in the first element of the ordered pair you cannot see. Okay, so that is what for the function and for relations. And for a function, it's completely dependent upon the input. If I give here 3, then the output will be also 3. Based on the input, when the output is also there for a function. Okay, but for a relation, it's not like that. Just multiplication of two different sets, we can say. Okay, so yeah. Next is, we are going to check about what so domain, codomain, and then all those things is we will be checking in. We will be seeing in function itself. Okay, very very clearly. Now we will be checking about inverse. Okay. So we will be checking about inverse relation, then number of relations. For that we have got a formula. Then we will be seeing about void relation, all those types of relations we will be checking now. Inverse relation. So what is an inverse relation? For example, if let this one relation be 1 comma 2, then 2 comma 3, then 1 comma 3. Okay, so let this be the relation. So for those who papa. Okay, so for those who already know this one, okay, already who have studied this lesson, they know that this is a transitive relation. Okay, for those who don't know, don't worry, in the next slides we'll be checking it. Okay, so the inverse of this relation is going to be just put reciprocal of every order decay. That will be 2 comma 1, that will be 3 comma 2, and that will be 3 comma 1. Okay, this is what their relation is going to be. Perfect. Okay, inverse relation is going to be. Next is domain. Okay, void relation. Okay, so before going into, okay, we'll first check about types of relations. Next is void relation. So what is a void relation? So void relation is nothing but if you are just multiplying two same sets, okay, A into A, then this set, okay, this set is actually should be having this pi. Okay, this total set itself can have pi, or just multiplication will be having pi, where pi belongs to A into A. For an example, okay, for an example, I will say that R, okay, where the relation is that A minus B should be greater than, okay, should be greater than 10. Okay, sorry, or yeah, 12 is given. Okay, so 12 where, okay, for all A comma B belongs to so belongs to A. This is the relation. Okay, and they have given the set. Okay, this is the relation, and they have the set that they have given is that 1 comma 2 comma 3 comma 4 comma 5 comma 6 comma 7 comma 8 comma 9 comma 10 they have given. Okay, so here the thing is they can just say that, yeah, so 10 minus 1 is the greatest number it can be. Okay, so that will be 9. So I will be saying that this has to be greater than 9 itself is okay. Okay, so there won't be any relation. Here there is no relation. A into A here represents, A into A here represents the relation. Okay, so see the relation here is null set. Okay, the relation that is here is null set. Okay, next, Papa, please. As I said, for some reason my bird just doesn't like my leg. Okay, now we will be checking about universal relation, identity relation. So what is a universal relation? See, let A be set A into A. This is what the condition is. Okay, if you are multiplying same set A into A, then the total set should be coming. For an example, greater than minus 1 I can say. Okay, so should be greater than minus 1 I can say. For here, okay, sorry. Here let it be here as 9 itself. The same relation if I'm taking over here. Over here. Okay. delete and I'll put over there -1. Okay, so here also set is the same set which is A. So like this set is there. So for this, very simple. No matter what number you do, just this minus. See, A into A, right? So in the first place, I'm going to take 1, 1. Okay, I cannot write every set. Okay, 1 into 1, then 1, 2, 1, 3, like that will be going on. At last, it will be 10, 10. That alone I know. I'll just write it as 10, 10. Okay, so the very least number that could be in this total relation is that 0. Okay, it can be 0. If you just subtract these two, then it will be 0. So for this, you can just put every number. Okay, you can put every number. That is what is there. So for this is a universal set because every element is there. Okay, it is being repeated over here. Perfect. Then identity relation. What is this identity relation? It is that A, B is set, then the relation. So before going into this identity relation, I will also say the reflexive relation, then we will easily get with it, okay? So see, very simple. This identity relation is there and okay. So identity relation, the keyword for this relation is that all elements. For an example, let me take that a set. Okay, here is a set that is A, which is 1, 2, 3 is there. Then the identity relation for this is going to be, if they have given this as 1, 1, 2, 2, 3, 3, then this is actually said as identity relation. Okay, if you want to write it in terms of a relation, then we can say that 1 R1, 2 R2, 3 R3. Like this, you can write it as. Perfect. Okay, so actually the thing is, coming to identity relation, all the elements must be here. Okay, 1, 1, 2, 3, 3 must be here. And along with that, none other element should be there. Only these three should be there. But whereas for here, okay, for reflexive relation, 1, 1, 2, 2 and 3, 3 should be there. And also along with that, it can have, okay, it can also have it can also have 1, 3, 3, 1, like this also. Other elements, it can also have other sets, okay? Other ordered pair also it can have, okay? But these three are very sure. In identity relation, I will just write the definition over here. That is, no. Okay, if every element of A is related to itself, then it is identity relation. If every element of A okay, is related, every element of A is related, itself, okay, to itself, then it is known as identity relation. But whereas coming to reflexive relation, okay, if itself only, okay, this is what the keyword is, okay, itself only, all elements, that is what here I have written as every element, okay, and it is actually related to itself only, that's it, okay. But whereas for identity relation, it's not like that. If every element of set is related to itself, it is called a reflexive relation. Okay, that's it. Okay, the next is symmetric relation. Okay, so in case of symmetric relation, it's actually very simple. Wait. So that's enough. So coming to symmetric relation. What's symmetric relation? Element is there. Okay, for an example, let me take this as a set. Okay, or a relation. Okay, let me take this as a set. Wait. There is with this set. Okay, A is the set. 1, 2, 3, 4 is this set. Okay, then if you want to know it is symmetric, then see this is what the relation is. 1, 2 is there. Okay, then 2, 1 should be there. Okay, if it is like this, then we will say it as symmetric. Okay, and along with this also 3, 2 is there. Then 2, 3 must be also there. Okay, exact opposite terms must be there. Then we will say it as symmetric relation. Okay, and also it can also have 1, 1 also it can have. Okay, this is also symmetric relation only. Okay, or 2, 2 also it can have instead of 1, 1 like that also it can have. Okay, next is, but the thing is, if in case there is this ordered pair, okay, like this, if 1, 2 is an ordered pair in that relation, then 2, 1 must be also there. Okay, then only it is actually symmetric relation. Okay, next is transitive relation. Very important. Okay, and it is kind of a little bit harder. Okay, kind of tough than reflexive and symmetric. Is that transitive? Is that transitive? So what's this transitive relation? Transitive relation is actually, for an example, if there is set A, okay, 1, 2, 3, 4 is there, then this relation must also have 1, 2. Okay, there is actually this 1, 2, and there is another set that is like 1, 3. Then if it is having 1, 3, then it is set as transitive. Okay, for an example, wait, I'll be just saying this in another way. See, 1, 2 is there. Okay, in this relation, 1, 2 is there, 1, 3 is there, then 2, 1 is there, then 1, 1 is there. Then like this, okay, relation is there. Okay, this is what the relation is. Okay, so 1, 2 is there, and 2, 3 is there. Then you have to exclude these two and you have to combine these two. Okay, for an example, if A is related to B, okay, then B is related to C, then A should be also related to C, then A should be also related to C, then only it is said as transitive. Okay, then only it is actually said as transitive. Okay, that's it. Next is number of relations. Okay, number of relations is that 2 to the power of n. 2 to the power of n is the formula for number of relations. Okay, where n a into n b. For an example, there is this A set which is having 5 elements and this B set which is having 2 elements. Then the total number of relation is that 2 into 2 to the power of 5 into then 2 to the power of 2. Okay, like this it has to be. So 2 to the power of 10. Okay, 2 to the power of 10 is what number of relations are. Okay. Next is number of equivalence relation. So what is equivalence relation? If there is a relation, okay, a relation is there, okay, where this relation is actually reflexive, symmetric, and then it is also transitive. Okay, and also it is transitive. Okay, so then if in case all these are there, then we will be saying this as equivalence relation. Okay, then we can say this as equivalence relation. Okay, so for number of equivalence relations, what we can say is B. Okay, we will be representing that with B only. Okay, with B only will be representing. For an example, there is a relation, okay, that relation is actually having 3 elements in it, 1, 2, 3, and they have said that this is actually equivalence. Then how many equivalence relations are there? Then B3, yeah, so B3, okay, you have to just by heart a few values, that B3 is equal to 5, B2 is equal to 2, B1 is equal to 1, B0 is equal to 1. Okay, just by heart all these 3 values. Okay, then the formula for number of equivalence relation is that B, how many elements are there? See, let me also take 4 over here. Okay, so B, 4 elements are there. Okay, so that means you have to write it as summation of, okay, B. Okay, so it is going to be just a summation of k n is equal to 0 and then b n k c n. Okay, lower limit, upper limit summation, that is what is here. Okay, see, first how you have to write it is, okay, so you can write it as, okay, yeah, so n only, okay, so n only will be there. Okay, for an example, see, here 4 elements are there, right? So it's going to be B4, which is, see, so you have to here start to substitute it. Before starting to substitute, what you have to do is you have to subtract from this 4 minus 1, that is 3, and you have to add, like this you have to write. This 4 can be written as 3 plus 1, right? Okay, like this you have to write, and then you have to start with the sums. Okay, so this 4 has to be written like this, and then you have to proceed with the sums. So how will you do? Okay, here it is at B0, okay, B0 and 4C0, like this you have to write. B0 4C0 plus B1 4C1 plus B2 4C2 plus B3 4C3 plus B4 4C3 plus B4 4C4 till like this you have to write. Okay, since here 4 is there, you have to write like this only. Well, if you ask me, why is there 4 plus 1? Four not 3 plus 1. So here you have to actually proceed with the 3 only. Okay, just write 3, 3, 3. Okay, till here even you have to end. Okay, that means just this number is there, right? So for those number alone you have to put. Okay, so B0 is equal to 1, that I have already given. Okay, so into 1C0. Okay, so it is actually NC0, which is actually into 1 plus, see, here it is actually, here it won't come. Right, instead of writing over there, I've written there. Okay, so yeah, so next is B1 is also 1 into 3C1. Actually, it is actually NC1 now. So NC1 means it will be just 3 plus B2, which is actually 2 into 3C2. So what is 3C2? Yeah. So 3C2 is 3. Actually, even I can do over board, but I'm feeling kind of lazy. Okay, 3C2 can be written as 3C1 itself. So which is actually 3C1 means NC1. So NC1 is N only. So which means here it is 3 plus B3 is 5. 5 into 3C3. So what is 3C3? 3C3. So NCN. So NCN is 1. Okay, so 1 plus 3 plus 6 plus 5, which is 15. Okay, which is 15. Just know these points. NC, I normally forget, but if you get to your remembrance now, then it's very good. NC0, NC1, NCN, NCN. These are those three terms that you have to remember. So, what are those three different terms? Is the question. So, NCN is 1. This is N. Okay, this is also 1. NC0 is 1. So, yeah. That's it. Okay, wow. So now we have completed totally this relation topic itself. Till function is there, that we'll be seeing in next video. Okay, thank you. Bye bye.